Okay, the Earth is going to melt. Different ways it melts. We talked about three different ways, three different reasons why. Then it's going to either intrude or going to extrude. So that gives us already two different kinds of rock types, the intrusive kind, the extrusive kind, but also the magma can have different chemistries. We look at the chemistry mostly in terms of these oxides. So there's a list here. Silicates, silica, SiO2, aluminum oxide, iron oxide, calcium oxide, magnesium oxide, sodium oxide, potassium oxide. So the proportions of those oxides in the magma matters. The one we focus on is the silica, the SiO2. So classifying igneous rocks is really based on how much silica is in the magma that forms the rock, and then is it intrusive or extrusive, because that's going to determine the size of the crystals. So this scale here at the bottom is saying a rhyolite, that pinkish rock, has, that's back. The arrow was backwards. I must have flipped it when I was editing the slide. Okay, it's fixed now. Okay, from a gabbro to a diorite to a rhyolite, that is increasing silica in that direction. A rhyolite has way more silica than a gabbro. There are different ways that occurs. In addition to the oxides and other cations in that magma, there are going to be gases. So magmas can be wet or dry. Volatiles here again sometimes just means water. Volatiles means like what can evaporate off. So here's a list of the different volatiles, like water vapor. Up to 50% of the volatiles in a melt would be water vapor, but also carbon dioxide, sulfur dioxide, nitrogen, and hydrogen. Those are all gases dissolved in that melt. That's going to matter later when we talk about volcanoes. Okay, so I mentioned how silica is really the basis for classification, and here are the classification words: felsic, intermediate, mafic, and ultramafic. So felsic means that a magma has a lot of silica in it, the SiO2. 60 to 76% of the molecules in that magma would be silica. So felsic rocks that come from that magma are going to be high in feldspars and potassium feldspar and quartz. They're going to be light colored, like the image down here down below. That's Yosemite again. A rock that is richer in magnesium and iron is going to be mafic. The felsic, the FeL and the SiC, comes from feldspar and silica. Felsic, feldspar, silica. Mafic, the Ma and the Fic, come from magnesium and iron. Mafic, magnesium, iron. That has way less silica in it, about half, 45 to 52%. Ultra mafic, meaning way mafic, way more magnesium, way more iron, is going to be as low as 36% silica up to 45. So those are going to be darker colored rocks that have, more magnesium and iron in them. How do we get that? Well, the melting of the magma is, let me stop the dogs from. Okay, the different chemistries are going to be related. Okay, we have different chemistries, different amounts of gas, and that is going to be dictated by a bunch of processes. What is the initial rock that's getting melted? That matters. How much does it melt? We call that partial melting. How much assimilation, that is the magma assimilating the rock around the magma chamber, the country rock or the wall rock. And then maybe mixing magma, two magmas mixing. And then we'll also talk about fractional crystallization at the end. Okay, each of those. So the source rock matters. If the source of the magma is the mantle, remember the mantle is already low in silica, higher in magnesium and iron. So that's where we would get mafic materials to create a mafic magma down from the mantle and ultramafic. If we're melting some of the crust has more silica in it, less iron, less magnesium, so we're looking at creating a felsic or an intermediate melt. All right, so partial melting. We're going to look later at Bowen's reaction series, and Bowen's reaction series is going to tell us that different minerals have different melting temperatures. It's like taking a pot, putting a fork and a stick of butter in it. The stick of butter is obviously going to melt first. The fork is going to take a lot of heat to melt. Minerals are the same way. We can mix a lot of minerals in a pot, and some of them are going to melt before others. Well, it turns out the silica-rich, higher in silica, those minerals melt first. So if we partially melt, only heat up a rock a little bit, we're going to drive off silica-rich magma, and those will crystallize into silica-rich igneous rocks. So if we only partially melt a rock, we're going to be getting a silica-rich magma, leaving behind those mafic minerals. So it's going to give us different chemistries of the igneous rocks. Meanwhile, as the magma moves through what we call the country rock, or the rock that was there, or through the wall rock, the wall of the magma chamber, it's going to be plucking off pieces of the magma chamber and assimilating or melting those pieces into that magma. So that's going to change the chemistry of the magma as it flows underground. Here's a picture of a xenolith. A xenolith is a piece of that country rock or the wall rock that didn't totally melt. It's just sitting there in the magma. Then the magma cooled and crystallized around the xenolith. So if that happens, it's not going to alter the chemistry. But for the most part, that xenolith would get melted into the magma assimilation. Okay, so now we've generated different kinds of magma. We partially melted. We grabbed pieces of the country rock or the wall rock. We've melted different sources. Now we have different magmas. And now what would happen if we mix two magmas? So magma mixing and the degree of mixing from one magma chamber to another can also give us different rock types. Okay, the last one. This is fractional crystallization. So just as the different minerals have different melting temperatures, right? If we start melting or heating up a rock, part of it might melt. There's also fractional crystallization where part of the magma will crystallize early in the cooling process, and then that magma then is going to change chemistries because you've pulled those cations or anions out of the system and you've changed the chemistry of the magma. That magma may move through the system then, and it's going to be a different chemistry as over here when it dropped out some other crystals. So here's in this diagram here, time 1, the original melt is mafic. The first crystals to form are going to be mafic ones. They have a higher melting temperature. They're going to crystallize sooner. And so the magma then over time is going to become more and more felsic as the mafic minerals, those higher in iron and magnesium, crystallize off. So the chemistry of the whole melt changes because parts of it are crystallizing and falling maybe to the bottom of the magma chamber. That goes right along with Bowen's reaction series. So in Bowen's reaction series, he did experiments on melting and cooling melts and determined that early crystals settle out, the ones that are mafic, and those are minerals with iron, magnesium, and the calcium-rich plagioclase. Left behind were minerals that were richer in silica, aluminum, and sodium. So he was able to set up Bowen's reaction series. And the reaction series has two parts. It has a continuous series that is the range of chemistries of calcium to sodium rich plagioclases. So there's high temperature and low temperature forming and melting plagioclases. Then there's also the discontinuous series where we're jumping from mineral to mineral, starting with olivine that is really rich in magnesium and iron, and then going down to quartz, which has just silica and oxygen in it. So let's take a picture. Let's look at a picture and see what that looks like. Remember, Bowen's reaction series, it's an idealized order of crystallization of minerals from a magma. Okay, here it is. On the right, there's that classification of the different magmas. Ultramafic at the top, mafic, intermediate, felsic. On the left side of the picture is the temperatures going from a high temperature, 1400 degrees, down to low temperature, 800 degrees. In the middle of the diagram, on the right side is the continuous series showing the order of crystallization of the plagioclase from a high temperature calcium-rich plagioclase down to a sodium-rich plagioclase. On the left side is the discontinuous series, starting with the cooling and crystallizing of the very mafic mineral olivine, which has magnesium and iron in it as a cation, and the anion is the silica tetrahedra, silica group, anion group. Going to a pyroxene, an amphibole, a biotite, feldspar, muscovite, and then quartz would be the last thing to crystallize from the magma. So that's Bowen's reaction series, idealized order of crystallization and temperatures of a magma.